7.8 Improper integrals. In defining a definite integral, the integral from a to b, f of x dx, we dealt with a function f defined on a finite interval, open bracket a and b, close bracket, and we assumed that f does not have an infinite discontinuity. Section 5.2. In this section, we extend the concept of a definite integral to the case where the interval is finite, and also to the case where f has an infinite discontinuity in open bracket a and b, close bracket. In either case, the integral is called an improper integral. One of the most important applications of this idea, probability distributions, will be studied in section 8.5. Figure 1, y equals, this sidebar, y equals 1 over x squared, and x equals 1 in the graph, and the area equals 1 minus 1 over t, and there's a point t on the graph. Back to the text, type 1. Infinite intervals. Consider the infinite region big S that lies under the curve y equals 1 over x squared above the x-axis and to the right of the line x equals 1. You might think that since big S is infinite in extent, its area must be infinite. But let's take a closer look. The area of the part of big S that lies to the left of the line x equals t, shaded in figure 1, is big A of t equals the integral from 1 to t, 1 over x squared dx equals negative 1 over x, an interval from 1 to t equals 1 minus 1 over t. Notice that big A of t is less than 1 no matter how large t is chosen. We observe that the limit as t approaches infinity of big A of t equals the limit as t approaches infinity of 1 minus 1 over t, close. The 1 minus 1 over t is in parentheses, and that equals 1. The area of the shaded region approaches 1 as t approaches infinity. See figure 2. So we say that the area of the infinite region big S is equal to 1, and we write the integral from 1 to infinity of 1 over x squared dx equals the limit as t approaches infinity of the integral from 1 to t, 1 over x squared dx equals 1. Figure 2, you have the interval from 1 to 2 on the x-axis, and the area equals 1 over 2. The other graph, it's from 1, x from 1 to 3, and the area equals 2 over 3. The area on the interval of x of the graph y equals 1 over x squared. From 1 to 5, the area equals 4 over 5. And the area from 1 to infinity, I guess approaching infinity, on the x-axis, the area equals 1. Using this example as a guide, we define the integral of f not necessarily a positive function over an infinite interval, as the limit of integrals over finite intervals. Definition 1 of an improper integral of type 1. Part A. If the integral from a to t of f of x dx exists for every number t greater than or equal to a, then the integral from a to infinity of f of x dx equals the limit as t approaches infinity on the integral from a to t f of x dx, provided this limit exists as a finite number. Part B. If the integral from t to b of f of x dx exists for every number t less than or equal to b, then the integral from negative infinity to b f of x dx equals the limit as t approaches negative infinity on the integral from t to b f of x dx, provided this limit exists as a finite number. The improper integrals, the integral from a to infinity of f of x dx and the integral from negative infinity to b f of x dx, are called convergent if the corresponding limit exists and divergent if the limit does not exist. Part C. If both the integral from a to infinity f of x dx and the integral from negative infinity to a of f of x dx are convergent, then we define the integral from negative infinity to infinity of f of x dx equals the integral from negative infinity to a of f of x dx plus the integral from a to infinity of f of x dx. In part C, any real number a can be used. See exercise 76. Any of the improper integrals in definition 1 can be interpreted as an area provided that f is a positive function. For instance, in case a, if f of x is greater than or equal to 0, and the integral from a to infinity of f of x dx is convergent, then we define the area of the region big S equals open curly bracket open x and y close is greater than or equal to a and 0 is less than or equal to y and y is less than or equal to f of x. In figure 3 to be big A of big S equals the integral from a to infinity of f of x dx. This is appropriate because the integral from a to infinity of f of x dx is the limit as t approaches infinity of the area under the graph of f from a to t.